Dear ladies and gentlemen, I may present a study about the determination of compression stress and volumetric weight of lightened concrete blocks with the use of recycled polymers and nanoadditives, work done by the Universidad de las Fuerzas Armadas ESPE in Ecuador. Traditionally, in the construction of masonry, materials from alluvial deposits are used, such as rocks and mud obtained from areas close to settlements for ease of transport. However, with time, the environment is being negatively affected as raw materials during the life cycle may irreparable ecological traces. The rate of extraction aggregates in the quarries increase every year. Therefore, researchers have seen the need to create the new raw materials that, in addition to being friendly to the environment, are resistant in relief structures, creating sustainability and sustainable development. Mixtures of polyethylene, terephthalate, PET, and cement for the protection of blocks have been developed, tested, and characterized. Hereby, an obtained final result has been a stable block with characteristics and functionality similar to traditional blocks, but replacing the materials that are extracted from the Earth's crust. Furthermore, an economical alternative with recycled materials from masonry elements has been presented with the purpose of reducing environmental pollution and increasing the strength of concrete blocks, concluding that the PET used in construction elements partially replace the aggregates of a conventional concrete, obtaining advantages such as the reduction of the specific weight and better thermal insulation. In Ecuador, there has been little research on the use of PET as an alternative material in construction. Nonetheless, there has been a study proposed of an innovative and ecological technology in the elaboration of aggregate for cobblestones in the city of Quito due to the large number of PET plastic bottles. The construction of construction materials whose mixing composition contains recycled PET saves costs and generates durability benefits compared to traditionally prepared materials. In addition, being a pollutant, residue of great amount of the planet generates a great environmental impact, so recycling should become a habit. The use of this recycled polymer generates new products that favor the construction sector, where the possibility of replacing crushed plastic with aggregates that are commonly used in the construction of construction materials is notable. A recent study demonstrated that the non-structural masonry concrete blocks used in several buildings in Ecuador do not meet quality standards because they present comparative strength below the minimum required by the regulation used. Therefore, the main objective of the current study has been to create a new material in which a percentage of polyethylene, tetrafluoride, and an additive is added over the original mixture with the aim of improving the properties in the masonry. In the norm NTE INN 3066 about concrete blocks within the grinds and test methods, it has been defined that the concrete blocks must be made with the hydraulic cement, fine coarse aggregates such as sand, gravel, split stone, volcanic granules, pumice, slags, and other suitable inorganic materials. The characteristics of the use of the sand size, shape, granulometric distribution, and texture must guarantee a uniform mixture, preventing the material from segregating, for which the fineness molecule must be in the range 2, 3, and 3.1, allowing the processed concrete to be manageable. Therefore, it is fundamental to control the amount of fine aggregate, as if the sand is insufficient, the mixture becomes rough, and or in the opposite case, when there is more, the mixture has a dry consistency, therefore more water will be required. Pumice rock is used in the production of lightweight and low-strength concrete depending on the degree of crushing of the material. Its porous texture causes the material to have a low density of 0.4, 0.9 grams per cubic centimeter, although it has a value, it values between 2.1 and 2.5 grams per cubic centimeter of specific gravity. It is commonly used in the construction of residential masonry because it insulates heat easily. In the current study, the stone material that was used in the manufacture of hollow concrete blocks was acquired from a block located in the Santa Teresa San Joaquin suburb, which receives the aggregates of Lazo Latacunga in north central Ecuador. The characterization obtained from the aggregates is presented in this table. The type of plastic that was analyzed is PET, a material that is easily found but generates a high level of pollution on the planet, as it is composed 60% petroleum, 23% of liquid derivatives of natural gas, and 30% of air. It is a chemical composition that does not allow to degrade rapidly, so it is advisable to recycle it. It was obtained from the Ecuador Industrial Plant, a company located in San Joaquin, and it's material that goes through a washing process, preventing the placement of polluting chemicals. This table lists the characterization of the PET plastic. This project also used a nanomolecular additive responsible for adhering the particles correctly generating new functionalities such as high level of resistance to the presence of UV rays and water. It also provides stability when the material is exposed to high temperatures. The American Concrete Institute is through tables to determine the proportion that meet certain characteristics. The concrete blocks were manufactured in this investigation as the dimensions of a hollow concrete block. The parameters and sizes are length 400 millimeters, width 150 millimeters, height 200 millimeters, partition thickness of 25, and wall thickness also 25 millimeters. Different dosages were performed in order to generate a concrete of dry consistency and with the ability to comply with the corrosion strength requirements established in the NTE-NEN 3066 standard. Pilot tests were conducted in order to reach an acceptable resistance before introducing plastic and additives into the mixture. The compression test applied at 7 days allows to obtain 70% of the resistance to make adjustment in the mixture if necessary. Once a dosage was corrected, 9 block samples were prepared for each dosage. In total, there were 126 specimens where in the first test, the amount corresponding to 10, 20, 30, 40, and 50% of TET were replaced, replacing the same percentage of sand. The amount of nanoadditive was determined by the ratio of 1 to 300 of the total volume of water. The blocks were made in the materials testing laboratory and according to the techniques used should be similar to those used in a block. Therefore, the fine, coarse, and crushed PET aggregates as well as cement were first placed in the concrete until visually or homogeneous color is obtained. Subsequently, water was added in 2 equal parts where the first has been to hydrate the paste and the second to control the workability and consistency of the mixture. The blocks need to be cured immediately after the elaboration so that the immobile specimens were left in the space between they were demolded for a day until they hardened. Then they were moved to a storage place where the climate conditions were adequate for the blocks to maintain their humidity and achieve maximum resistance. They were placed with a maximum separation of 2 centimeters between each specimen to ensure circulation. Prior to refraining, the blocks were submerged in water for a period of 2 hours, so the one-to-one dosing water were higher properly. This was placed in a 6 millimeters layer on the upper and lower face of the masonry, controlling its leveling in order to finish the mortar of the restraint was moistening to prevent cracking and to keep the moisture. Plastic covers were placed for a day. After 24 hours of curing of the restraint, the elements were proceeded to be tested, which were placed in a compression machine according to the position they were placed in the construction masonry. In addition, the vertical alignment was verified so the applied load is distributed throughout the contact area. This figure illustrates the result of compression resistance presented by the hollow concrete block in the first test, where it was observed that it increased favorably until reaching 20% of PET. However, by placing a percentage of crushed plastic and resistance decrease, then they are even lower compared to the compression effort that they obtained when testing the blocks without plastic. The greatest resistance was encountered in blocks that contain percentage between 10 and 30% of crushed PET plastic. The resistance results of the blocks containing a percentage between 20 and 30% of plastic in the mixture are shown when the efforts are increasing of up to 25% of PET. These values indicate an increase of 20% in comparison with the previous results, as the dosage that was used had an increase in cement and nanoparticle additive. In this figure, the optimal dosage is that which contains 25% PET plus nanoadditive and is presented the highest resistance result. With superior mechanical properties. With the compression results obtained in the current study, it can be defined that that by introducing different percentage of PET, plastic, and a certain amount of nanoadditive, with the resistance exceeds that of traditional blocks. In the case of volumetric weight, the specimens of the first test yielded a certain similarity between percentage of 10, 20, and 30% PET. Hereby, the obtained values they are reduced while increasing the amount of PET plastic. The lowest values were corresponding to the blocks of which are between 25% and 30% PET plus nanoadditive compared to the volumetric weight obtained in the blocks made without plastic additive. This figure illustrates that when reducing low density materials such as plastic into the block concrete mix, it influences the reduction of volumetric weights as the results obtained are lower than the value presented in the original blocks. In order to obtain the absorption results, the NTE-NEN 3066 standard was used, where first the whole blocks were immersed in water for 24 hours. Then the same mass of each specimen was recorded while it was submerged in the water with a wad of metal mesh held in a wire. The visible water was removed as shown in order to verify the surface dry mass. To end the test, all the specimens were placed inside the oven 24 hours. After the period of time, the dry mass of each sample was recorded. Now the bar graphs with the absorption of in kilogram per cubic meter and a scatter plot would line with absorption in percent. In the two conducted studies, it has been demonstrated that the absorption values tend to decrease with induced more percentage of plastic in the mix coinciding with, which indicate that the absorption and humidity decreases while the proportion of PET increases, as the plastic is composed of non-absorbent particles. For comparison purposes, compression and absorption tests were conducted on specimens that were made with only 25% PET, and some replacement were in samples in which the total amount of pumice was replaced by PET, plastic, and hollow concrete blocks. For commercial use, they have low resistance compared to the blocks that were generated. It can even be determined that the specimens with PET that do not contain additive and those that do not have pumice could be used in construction, coinciding with studies where blocks containing plastic due to their resistance cannot be used in structural masonry. Several studies mention that using recycled plastic aggregate in concrete reduces costs. However, in the current study, the unit price analysis indicated that these blocks contain PET are more expensive, as they may be an increase, especially that where needed to add more cement, or they are introduced new materials in order to contain a superior strength. The table lists with a cost of the block unit without considering indirect costs. However, a comparison was performed with compressive strength, water absorption, and cost in order to relate them to each other and determine the optimal dosage. This contains 25% PET in scent replacement and additive, and although it costs high, it generates the best results in both compression and absorption. However, it could also be considered the dosage with 25% PET in replacement of scent without nano-additive, and its result is acceptable and the cost is lower. In order to generate a reduction in the cost of entry, a daily production of 6,000 blocks was established considering the labor capacity of a worker, which implies an increase in both machinery and labor. However, when performing the new cost analysis, a maximum of 6% where blocks were reduced, listed in this table. In the conclusion, it is conducted a study where we can see that all the compression test performed in the hollow concrete blocks resistance were obtained lower than the minimum value of 40 kilograms per square centimeter, while the best results being 36.5 kilograms per square centimeter belongs to the dosage of 25% PET and a scent replacement of 1 to 250th of waterproofing and resistance improver nanoadditive, whose resistance compared to the blocks that are sold is very good, because these usually have an average of 14.3 kilograms per square centimeter, being well below the minimum value. The volumetric weights belonging to the percentage of plastic used were excellent, as all were light. So here are a few more conclusions, like the volumetric weight is not significantly affected in the pumice if used PET instead. It was also demonstrated that plastic quantities greater than 50% prevent water absorption, and it is considered that use PET next to another that is optimal, even less water is absorbed, as its combination allows a waterproof structure without pores. Here are a few more conclusions, and with this, I rest my case of our study of the PET plus nanoadditive to be cheaper than the usual.